Hello dear students, welcome to the lecture 4 of object-oriented programming. If you remember last week, our software was failing, was crashing when we were trying to write very big dictionary files with streamliner method. Uh, so I told you that in the previous week that we could fix it with let's say using subthreads, subtasks. So I did a test and it works. I am going to commit changes back to where it was on the GitHub on the lecture 3, end of lecture 3. Then I will show you the steps. So first I am going to open my page. One second. Okay, let's okay, I think it didn't log in. Okay. Okay, you see it didn't log in when I started from there, so that was the reason. Now it's logged in. Now I will revert it back to where it was in the last comment. I think this should work. Okay, untracked files are still there. Yeah, okay, it's fine. Untracked files can remain. I'm going to delete them as well. Okay, now it is reverted back to latest commit. So we are on the same page. If you remember, when I have added 10 million records and try to write them to the file with uh, uh, Streamliner, the application and everything was crashing. To prevent that, we are going to use tasks. Okay, so tasks using. I'm going to add it to second window. Okay, it is in the system threading namespace, and these method calls will be encapsulated in Task Factory. Okay, when I okay, training tasks. That's how I need to find it. Okay. So with this command, I'm going to start this with this command. I'm going to start this method inside a new task, a task that is independent from the main task, which is the task which runs main window and second window. So uh, you will get understand this as we show more examples. However, I will show you first for solving this problem in this case, and we will take this method from the main task into a subtask, into a new task. Maybe there are some good explanations. Let me find for you. Okay. Okay, I think this looks like a good article. So,
What is task in C#? .NET Framework provides threading, tasks class to let you create tasks and run them asynchronously. A task is an object that represents some work that should be done. The task can tell you if the work is completed, and if the operation returns a result, the task gives you the result.
okay, so what is thread?
What is thread? .NET Framework has thread-associated classes in system, threading namespace. A thread is a small set of executable instructions.
Okay, why we need tasks?
It can be used whenever you want to execute something in parallel. Asynchronous implementation is easy in a task, using async and await keywords.
Okay, why we need a thread?
When the time comes when the application is required to perform few tasks at the same time.
Okay, and yeah, this article is not a good example. Let me. Okay, let's read the threading model. This will help you to understand threading model.
Windows Presentation Foundation (WPF) is designed to save developers from the difficulties of threading. As a result, the majority of WPF developers won't have to write an interface that uses more than one thread. Because multi-threaded programs are complex and difficult to debug, they should be avoided when single-threaded solutions exist.
Okay.
No matter how well architected, however, no UI framework will ever be able to provide a single-threaded solution for every sort of problem. WPF comes close, but there are still situations where multiple threads improve user interface (UI) responsiveness or application performance. After discussing some background material, this paper explores some of these situations and then concludes with a discussion of some lower-level details.
Overview and dispatcher. Okay.
Typically, WPF applications start with two threads, one for handling rendering and another for managing the UI. The rendering thread effectively runs hidden in the background while the UI thread receives input, handles events, paints the screen, and runs application code. Most applications use a single UI thread, although in some situations it is best to use several. We'll discuss this with an example later. The UI thread queues work items inside an object called a dispatcher. The dispatcher selects work items on a priority basis and runs each one to completion. Every UI thread must have at least one dispatcher, and each dispatcher can execute work items in exactly one thread. The trick to building responsive, user-friendly applications is to maximize the dispatcher throughput by keeping the work items small. This way items never get stale sitting in the dispatcher queue waiting for processing. Any perceivable delay between input and response can frustrate a user. How then are WPF applications supposed to handle big operations? What if your code involves a large calculation or needs to query a database on some remote server? Usually, the answer is to handle the big operation in a separate thread, leaving the UI thread free to tend to items in the dispatcher queue. When the big operation is complete, it can report its result back to the UI thread for display.
Okay, so let's run the application and remember what was the issue last time we were trying to solve. Okay, currently our program is basically a synchronous program, not asynchronous. It's a synchronous program, which every method and everything runs on the main thread. Okay, see there is no other threads we have started. Everything on our software runs in a single threaded mode, and therefore, let's say when I click generate 10 million records here, my UI thread will freeze. Okay, because since I am running everything in the main thread, it blocks my user interface as well because it is running in the same thread, and my user interface becomes unresponsive. Let me show you what I mean. Currently, when I hover my mouse over these buttons, you see they are getting highlighted, and after I click generate numbers and add to dictionary button, it will start processing that command here until this method is completed. The whole thread will be blocked because thread will be waiting this execution, this method call to be completed because they are running in the same thread. Okay, so the thread will be blocked. Uh, watch closely. You see now it is frozen. You see now this is let's say frozen as highlighted, and these were not clickable. And when the task is finished, when that button click event is finished, thread returned to normal. Okay, and so this is the meaning of having different threads to tend different items. Okay, let's continue reading. Okay. When I hit the generate numbers button, thread become unresponsive. Okay.
Historically, Windows allows UI elements to be accessed only by the thread that created them. This means that a background thread in charge of some long-running task cannot update a text box when it is finished. Windows does this to ensure the integrity of UI components. A list box could look strange if its contents were updated by a background thread during painting.
Okay, let's read this as well.
WPF has a built-in mutual exclusion mechanism that enforces this coordination. Most classes in WPF derive from dispatcher object. At construction, a dispatcher object stores a reference to the dispatcher linked to the currently running thread. In effect, the dispatcher object associates with the thread that creates it. During program execution, a dispatcher object can call its public verify access method. Verify access examines the dispatcher associated with the current thread and compares it to the dispatcher reference stored during construction. If they don't match, verify access throws an exception. Verify access is intended to be called at the beginning of every method belonging to a dispatcher object.
Let's continue.
If only one thread can modify the UI, how do background threads interact with the user? A background thread can ask the UI thread to perform an operation on its behalf. It does this by registering a work item with the dispatcher of the UI thread. The dispatcher class provides two methods for registering work items, invoke and begin invoke. Both methods schedule a delegate for execution. Invoke is a synchronous call, that is, it doesn't return until the UI thread actually finishes executing the delegate. Begin invoke is asynchronous and returns immediately.
Okay, so you are starting to get an idea of separating tasks, and now we are going to read tasks. Let's find the task class. We will get back to return to dispatcher to update UI. Okay, so let's read the task.
The task class represents a single operation that does not return a value and that usually executes asynchronously. Task objects are one of the central components of the task-based asynchronous pattern first introduced in the .NET Framework 4. Because the work performed by a task object typically executes asynchronously on a thread pool thread rather than synchronously on the main application thread, you can use the status property, as well as the is cancelled, is completed, and is faulted properties, to determine the state of a task. Most commonly, a lambda expression is used to specify the work that the task is to perform.
So the keyword here is on the main application thread. Currently, everything is running on the main application thread. So to prevent that, I am going to take this into a subthread and therefore prevent application interface freeze. Okay. Okay. And if I call this method like this, it will be still running in the application thread. Okay. And so I am going to call this method in a task. How do I do that? I click task. See now the task class is available. It is under system threading task and task. You see it says represent an asynchronous operation. It can be await. It is awaitable. However, we don't need await right now. Task factory. Okay. So Task Factory provides access to factory methods for creating and configuring task and task key result instances. A factory object can create a variety of task and task key result objects. Okay. And I'm going to say start new. So with this method, I am going to start a new task, a new action, as you can see. So this action will be like this, and however, I am going to use self action this way, and it will be with lambda expression this. So whatever I write here will be run in the thread pool, in a different thread than the main thread, and since it will run in the different thread, it will not block the user interface, the main thread. Okay, so I'm going to get this method inside here. So it will be running in a different thread. We can also check this by, let's say, okay, okay, probably this will work. Okay, I am going to write this to the console window, Debug.WriteLine. Okay, so Debug.WriteLine will put and will write whatever we provide to do this window when the application is running in the debug mode. And here I am going to write another one. So let's put a breakpoint here and run the application. Oh, I have to make this assignment again here. Okay, and click button. Okay, so let's see the output. Okay, the output window is here. So the current thread ID is 1. You see it, 1, which is the main thread, and when it comes inside the task factory start new, it becomes 4. So here it is using thread ID, let's say thread that has ID of 4 in here, and it is using the thread ID thread that has ID of 1, which is main thread. So when I run the application, it will not freeze this time. However, it will throw an error when it tries to update user interface. You see, the colon thread access this object because a different thread owns it. So why our application crashed? Okay, I started a new, different subthread and run the operation inside that thread. Let's run it again for, let's say this time 20 million items, so you will understand what I mean. I hope the computer will not crash. Okay, let's close some tabs to open some uh, RAM memory. Okay, so it is going to generate 20 million items and add them to the dictionary. However, this time our user interface, this will not frozen. It will be still responsive because we are going to use a task factory to start method call inside a different task. Okay, that's right. Okay, you see it is still responsive, RAM memory usage increases because the method call is running, and at the end it throws an error. Why? Because the calling thread cannot access this object because a different thread owns it. Which object it cannot access? It cannot access the object list box statics item clear. So what I'm going to do is I need to try to access user interface from dispatcher, which we have explained it. Actually, which this thread explains here. Let's read more.
The dispatcher orders the elements in its queue by priority. There are 10 levels that may be specified when adding an element to the dispatcher queue. These priorities are maintained in the dispatcher priority enumeration. Detailed information about dispatcher priority levels can be found in the Windows SDK documentation.
Okay, so what we need to do is add this list box item access inside the dispatcher. So it is called as dispatcher. It's the system Windows threading dispatcher, system Windows threading dispatcher object dispatcher. Okay, so you see it has this icon, and then I am going to say begin invoke. I can also call invoke. However, if I call invoke, it will freeze the UI until the operation is completed. However, I am going to say begin invoke, so it will be executed whenever possible. So it requires a new action, and it's almost same. Let's say new action. Okay, then we type delegate. You don't need to know what they mean at the moment, but this is the format how it runs. Okay. So this way, uh, whatever the objects we try to access and modify in the UI inside here will be handled by the dispatcher thread. Okay, so let's put it here, and I am going to get thread ID again and write the thread ID. Let's see what will it output. This time our application will uh, work fluently without user interface being frozen and without throwing any error. So what we have done, we have called this method inside a new task by using Task.Factory.StartNew. So this is asynchronous, multi-threaded application programming, and dispatcher we will access the UI elements. So I'm clicking generate numbers. You see the RAM memory usage increases, and meanwhile the dispatcher updates its interface. There's a very slight, let's say, very slight UI freeze for a short period of time, because when the dispatcher class updates the user interface, it freezes the user interface for a moment. And you see current thread ID was 1 when we called the current thread managed ID here, you see, and I am seeing it from the output window, and current thread ID was 4 in the task factory method here, so it used a task from thread pool. It starts a task in the thread pool, and it becomes thread ID 1 inside dispatcher again. Why? Because dispatcher running in the main thread. Okay, you see, it is 1 again. However, in here, it will be 4. Why? let me show you, because this will be followed by the task started here. Let's say click it. I'm going to remove this. Okay, this should be for again, because this method is being called, being executed by the task here. Okay, so they should have same task ID. Let's also write here. You will understand. Okay, let's run the application and see the output. Okay, so when the generate button click it, the thread ID is 1. When the thread inside the task factory, the thread ID is 4. Inside generate random numbers method, the thread ID is 4, because this let's say this thread called this method. And inside update statistic methods, here it is still 4, and inside the dispatcher begin invoke it is 1. So this is how multi-threading is done. Basically, this way you can use all CPU cores of your computer. You can run tasks in parallel. For example, I will show you what I mean. Okay, currently this will run this one at first, then run this one at second. Okay, so it is still asynchronous. I am going to add all of this inside task factory start new as a new task, starting a new task. Okay, let's make each one of them as a new task. So these two method call will be executed in at the same time in parallel right now. And this time, okay, this way. Let's make this 10 million again and see. Uh, this time the application should not crash like in the previous lectures. And case 4 was, okay, there were no case 4. Okay, so you see application interface is still running very smooth, and it pauses for a moment while updating this interface. Okay, and then I am going to write all lines method to see how much time it takes. Okay, you see interface is still not frozen. This is opened immediately and the output file is still not generated. Why? It is because okay. Oh, we are trying to update the list box here, so that causes another error. We need to take this inside dispatcher. However, I am going to write a method to do that. You should make everything method calls and never write copy pasted code. Okay, so this will be Oh, we don't need this. It is like this, and another here. Okay, so what is this going to take it here and the message? Let's say here. Okay, so I am going to make this method call here. It will be the message first and the insert index last. Okay, so this will be always thread safe because it uses dispatcher begin invoke, and we will update every one of them like this. So you see we have avoided writing the same dispatcher code again and again, and we made them let's say method call Okay, let's run the application again. This window is opened immediately before the application completed. Why? Because if we check the uh, calls here, this task starts. However, uh, the main thread, or let's say the task called this method, doesn't wait because this task starts and it continues executing whatever next. So whatever next is here. So it's let's say run this and then run this. Okay. So actually we can prevent these to be run it immediately to how we can make that. We can make it like this. I'm going to like this, and I am going to edit as continue with. Okay, and continue with take a new task, new action, or I don't know the exact syntax. Okay, I think there is. So the name completed means the task that returns as a result of this start new. You can give any name. You say it's. You see it is parameters. The completed task parameter. We can make it like this. Enter. And let's add them to here and here. So whenever this task is completed, it will call, it will execute the final task method here. So we have made them to continue with. Okay, and this time it should work. Let's run it. You see, you can read such documents and check the examples. There is also you can see this in English. Let me show you how to do that. Or okay, I couldn't find it anyway. So I am generating numbers. The interface is you see brilliant, but interface is pausing for a moment. Do you know why? It is not because the interface is getting updated. It is because the let's say orders or the commands we execute here, order by and order by descending, these are taking time. And since every one of them is running in a single dispatcher begin invoke, the dispatcher becomes, let's say, unresponsive. Okay, that is why. However, I can calculate every one of these statistics inside another method and update the interface at one run, and that time the interface wouldn't be stopping. Okay, so this is why the interface is being paused. The reason is not updating the interface. The reason is method calls, orderings here, and the calculations here. This is what takes time, and during that time the interface become unresponsive. That is the reason. I will also show you that after we see the writing. Okay, so let's use write all lines method, and it will open the folder when everything ends. Let's write to the file. You see nothing appeared here. It will appear once the whole entire file is written. Let's check the performance. Okay, I will write it again. I'm going to delete this and write file to this dictionary. Okay, let's check the disk activity. Okay, you see it is writing 100 megabytes per second and it is written at once. So meanwhile, if I close the application, it will file will not be completely written to the let's say hard drive. Okay, the current RAM usage is pretty low because we have manually pulled garbage collector after the task is executed here. And let's call streamwriter method. This time there will be two files immediately generated. However, one method will write immediately, uh, one method will flush after reading all, and the other method will flush constantly. Okay, you see auto flush file and no auto flush file. No auto flush file will be quickly written in a batch. Okay, no auto flush file is done because meanwhile your application crashes when no auto flush file is uh, when you are not using no auto flush, you will lose data. However, with auto flush, it is writing the data, let's say constantly to the text file. Okay. So whenever I open this file, it will be updated. Let me show you. I hope the okay. So it has currently 4 million lines, and if I open it again, so it has now 4.7 million lines, and if I make it like this, it will say updated again, and it has 5.3 million lines. You see, it is constantly updated. Whenever click refresh button, you will see exactly This will be refreshed. Okay, you see it is getting refreshed. Whenever I click properties, it is getting refreshed because it is constantly flashing the stream writer and writing to the text. It is taking too much time. However, it is a different approach to write to file. As you can see, the application didn't crash. It didn't even become unresponsive. It is working perfectly fine. However, it is taking some CPU. So depending on your computer properties and task you need to complete, uh, you can choose whether use auto flush or not. Uh, okay, the job is finished. So write file with all lines took about 10 seconds. Write with streamwriter no auto flush took about 8 seconds. We have a naming error here. Write string builder. Oh, we didn't run the string builder method. Let's call it again. Call it 2. You see, it will also take everything into the RAM, memory, and write all at once. Okay, the string builder method took the least duration. So as I said, depends on your uh, let's say needings. Okay, so I'm clicking generate more numbers and you will see the interface will freeze meanwhile updating the statistics. Okay, it is frozen right now, still frozen, and it is back to responsive. You can also prevent this. How can we do that? We can do that easily by calculating this statistic inside another method call. Okay. How am I going to do that? Is simple. I'm going to write a new uh, method, and instead of list box statistic, this will return a list. Okay, I'm going to put back inside here, and I'm going to change list box statistics to list statistics. Okay, and it will return this one, and of course list doesn't have items method. Okay, and I'm going to call this method here and assign it to a new list. Then here I am going to use for each. Okay, this time you will see almost no interface unresponsiveness. It will be responsive all the time because statistics will be calculated at the subthread and interface will be updated immediately. Let's try using never freezing, never freezing. Okay, no freeze, no freeze. You see, it never frozen. I'm clicking again, you see no freeze. It is responsive, responsive, responsive. Okay, you see it is immediately updated because we took the uh, CPU intensive task to the background task. Okay, we took the CPU intensive workload to a subthread. We took the uh, job from main thread to a subthread. So this is an CPU intensive task. So you should also do the CPU intensive task in different threads than the main thread, and therefore keep your user interface always responsive. This is really important. Okay. Okay, so we have shown everything, and then we can start another project. I'm going to update recent changes as lecture 4, so you can compare commits. Let me show you that as well. Let's remove these outputs because they will take forever to upload GitHub. Okay. Okay. All right. Now when we open our GitHub, you will see the recent commit, and you can compare what it has made. You see there are 14 commits. You see lecture 4 part 1 changes and improvements. When I click that, it shows what differences we have made. You can also download and switch to each commit. How can you do that? I will show you that. So you can work at home and see different commits. I'm going to clone this into a new, let's say, folder. I'm going to commit it into my C drive. How am I going to do that? I am starting another git bash. Okay, it didn't log in, so open a logout one. Okay, it has logged in. I'm going to move to C drive, and I'm going to call git clone URL of our repository, not this one though. Okay, let's open the correct one. Okay, it is here, correct repository, and I'm pasting. Okay, so it is cloning the entire repository into the C with name, folder name like this. Okay, currently it is like we have made. Let me show you. the last time we have committed. It will be same as the last time we have committed. Okay, it is loading the references. When I open the source code, okay, you see it is same as what last time we closed the application. So I want to return it to the lecture 3, not lecture 4. How can I do that? How am I going to do that? I'm going to do that with this way. So you are clicking the commits and it will show you the ID of commits. So lecture 3 commit was this one. It is shown here. When you click it, you see the head of the commit here. Okay. So this is the commit ID. Then you move inside that folder with git bash. Watch here closely. Now I am the inside of that folder. Then I am going to type as git checkout and commit ID. Okay, so now it has checked out into that particular commit, and when I click here, it will auto reload whatever there was. You see, this is the way we have left it as lecture 3. You see all those changes gone, the recent changes gone, and now my project is same as lecture 3. I can return back to head. How can I do that? You click out head. Okay, now it is back to the, oh, not head. Maybe, okay, master. Yes. And okay, it is reloaded again. You see now it is again same as lecture 4. This is how you can return your application to the previous commits with git bash and github. Okay, I'm going to close them and delete this folder. Okay, you see it shows there are still some items hanging in the memory, and that prevents me to delete this folder. But it's not a problem because we are going to compose a new project. Okay, I'm going to start a new VPF project. Create new project. I am going to name it. I am going to select VPF.NET Core. Next, I'm going to select my project folder here and source codes and lecture 4. I'm naming it as lecture 4. Okay, this box text box object shallow cloning object deep cloning. Okay, so let's start with shallow cloning and deep cloning and what they mean. So in C# every objects or every class objects, let's say every objects that is not a class, uh, that is a class actually, not a struct, is kept with references. Okay, let's see, maybe there is a good explanation. It is hard to explain it with talking. Okay, so in C Sharp, actually Microsoft.NET, uh, An object can be either value type or reference type.
Types in Microsoft .NET can be either value type or reference type. While value types are stored generally in the stack, reference types are stored in the managed heap. A value type derives from system value type and contains the data inside its own memory allocation. In other words, variables or objects or value types have their own copy of the data.
Okay, this is important. I will explain it with
A
examples.
reference type, meanwhile, extends system object and points to a location in the memory that contains the actual data. You can imagine a reference type similar to a pointer that is implicitly dereferenced when you access them. The built-in reference types supported by C# include object, string, and dynamic. All fundamental data types, Boolean, date, structs, and enums are examples of value types. Examples of reference types include strings, arrays, objects of classes, etc. To create reference types in C#, you can take advantage of these keywords: class, interface, and delegate.
Okay, this is important. Let's continue.
Note that unlike a reference type, you cannot derive from a value type, nor can you assign a null value directly to a value type. You can assign a null value to a value type only by taking advantage of nullable types, a feature added to the newer versions of .NET Framework. When a value type is copied to another, the value is copied. Hence, you can manipulate the values in them independent of the other. A change in one doesn't affect the other. On the contrary, when you copy a reference type to another, the reference is copied. If you change one of them, the other is also affected. As an example, if one of the reference is set to null, the other also becomes null.
Okay, storage locations.
The CLR stores objects in three types of storage locations: the registers, the stack, or the managed heap. While the short-lived objects are stored inside registers or stack, the long-lived objects are stored in the heap. As I mentioned earlier, value types are generally stored in the stack.
So what is CLR if we wonder? CLR is the Common Language Runtime, and let's read it on the Wikipedia.
The Common Language Runtime (CLR), the virtual machine component of Microsoft .NET Framework, manages the execution of .NET programs. Just-in-time compilation converts the managed code, compiled intermediate language code, into machine instructions which are then executed on the CPU of the computer. 1. The CLR provides additional services including memory management, type safety, exception handling, garbage collection, security, and thread management. All programs written for the .NET Framework, regardless of programming language, are executed by the CLR. All versions of the .NET Framework include CLR. The CLR team was started June 13, 1998.
Okay, you see there are versions of CLR, and this is how it is done. Let's continue.
It's a common misconception that value types are always stored in the stack. I would rather say that value types can be stored in the stack when the variable is either a temporary variable or is a local variable and the JIT compiler decides not to enregister the value. In essence, the actual location of a value type depends on the implementation of the JIT compiler. Note that a value type can be stored in a stack frame, in the CPU register, or even in the heap memory if the value type is contained inside an object, i.e., if it is a part of a reference type. On the contrary, reference types are stored in the GC heap. The reference is stored in a stack while the object is allocated in the heap.
Okay, so what is GIT if you wonder? Okay, so GIT is translating uh, language code into the native matching instruction. Okay, let's read this.
Code is compiled into the Microsoft Intermediate Language, which is similar to assembly format. When you double-click an executable, Windows loads mscoree.dll, which then sets up the CLR environment and starts your program's code. The JIT compiler starts reading the MSIL code in your program and dynamically compiles the code into x86 instructions, which the CPU can execute.
Okay, so it is just-in-time compiler. Okay, you can look every one of these things with details at your home.
Instances or references of a value type are stored in the stack, the register, or in the heap depending on whether the lifetime of the instance or the reference is short-lived or long-lived. A value type can reside on the stack if they are local variables and in the managed heap if they are fields of a class, i.e., they belong to or are a part of a reference type.
Okay, we will make more examples. So one more thing. Okay.
Differences between stack and heap. Stack is used for static memory allocation and heap for dynamic memory allocation, both stored in the computer's RAM. Variables allocated on the stack are stored directly to the memory and access to this memory is very fast, and its allocation is dealt with when the program is compiled. When a function or a method calls another function which in turns calls another function etc., the execution of all those functions remains suspended until the very last function returns its value. The stack is always reserved in a LIFO order. The most recently reserved block is always the next block to be freed. This makes it really simple to keep track of the stack. Freeing a block from the stack is nothing more than adjusting one pointer. Variables allocated on the heap have their memory allocated at runtime, and accessing this memory is a bit slower, but the heap size is only limited by the size of virtual memory. Elements of the heap have no dependencies with each other and can always be accessed randomly at any time. You can allocate a block at any time and free it at any time. This makes it much more complex to keep track of which parts of the heap are allocated or free at any given time. You can use the stack if you know exactly how much data you need to allocate before compile time and it is not too big. You can use heap if you don't know exactly how much data you will need at runtime or if you need to allocate a lot of data. In a multi-threaded situation, each thread will have its own completely independent stack, but they will share the heap. Stack is thread-specific and heap is application-specific. The stack is important to consider in exception handling and thread executions.
So stack is thread specific and heap is application specific. Just a moment ago, we have shown you the stack and we have shown you threads and application. But I will pause for a moment. Okay, so let's see if there is another description. Okay, let's read this.
Even though with the .NET framework we don't have to actively worry about memory management and garbage collection (GC), we still have to keep memory management and GC in mind in order to optimize the performance of our applications. Also, having a basic understanding of how memory management works will help explain the behavior of the variables we work with in every program we write. In this article, I'll cover the basics of the stack and heap types of variables, and why some variables work as they do. There are two places the .NET framework stores items in memory as your code executes. If you haven't already met, let me introduce you to the stack and the heap. Both the stack and heap help us run our code. They reside in the operating memory on our machine and contain the pieces of information we need to make it all happen. Stack versus heap, what's the difference? The stack is more or less responsible for keeping track of what's executing in our code or what's been called. The heap is more or less responsible for keeping track of our objects, our data, well. Most of it, we'll get to that later. Think of the stack as a series of boxes stacked one on top of the next. We keep track of what's going on in our application by stacking another box on top every time we call a method called a frame. We can only use what's in the top box on the stack. When we're done with the top box, the method is done executing, we throw it away and proceed to use the stuff in the previous box on the top of the stack. The heap is similar except that its purpose is to hold information, not keep track of execution most of the time, so anything in our heap can be accessed at any time. With the heap, there are no constraints as to what can be accessed like in the stack. The heap is like the heap of clean laundry on our bed that we have not taken the time to put away yet, we can grab what we need quickly. The stack is like the stack of shoe boxes in the closet where we have to take off the top one to get to the one underneath it. The picture above, while not really a true representation of what's happening in memory, helps us distinguish a stack from a heap. The stack is self-maintaining, meaning that it basically takes care of its own memory management. When the top box is no longer used, it's thrown out. The heap, on the other hand, has to worry about garbage collection, GC, which deals with how to keep the heap clean. No one wants dirty laundry laying around, it stinks. What goes on the stack and heap? We have four main types of things we'll be putting in the stack and heap as our code is executing: value types, reference types, pointers, and instructions.
Okay, value types.
In C#, all the things declared with the following list of type declarations are value types because they are from system, value type.
Okay, so boolean byte. Let's copy this into the as value types. I'm going to open the code. Let's add a class. Class named as value types. And so what is the default value of boolean? We can test that. Is so byte. Every value type has a default value. So you see, enum doesn't have a default type, therefore you have to define enum like this. So it will be empty in this case. So the default type is 0. Numeric types are 0, 0, 0. This is like this, which is equal to character null. Let me show you what I mean. Zero, let's type and empty. So default 0, 0, 0. Struct cannot use it this way, I think. To use struct, I think it is defined as classes empty. Okay, so these are all value types. You see string is not here because it is class object. Okay, and we can add each of these into a object list and print every one of them to the screen if you want. Let's continue. So there is reference types. Really important to understand this.
Reference types. All the things declared with the types in this list are reference types and inherit from system, object. Except, of course, for object which is the system, object.
Okay, let's copy paste this as well. So you will have, okay, now interface is how we define interface. Okay, it is also like this. And delegate. Okay, we will see each one of these in the future lessons with examples. I'm just doing. So by default, this is null. Everything is by default null, by the way. Every one of the objects here is by default null. You see it says 0 references because these are reference types. And this is more like an object. So no references, this is also object and this is also object. Okay, so these are reference types and let's go pointers. There is also pointers.
The third type of thing to be put in our memory management scheme is a reference to a type. A reference is often referred to as a pointer. We don't explicitly use pointers, they are managed by the Common Language Runtime, CLR. A pointer, or reference, is different than a reference type in that when we say something is a reference type as a means we access it through a pointer. A pointer is a chunk of space in memory that points to another space in memory. A pointer takes up space just like any other thing that we're putting in the stack and heap, and its value is either a memory address or null.
And there is also instructions. Okay, how it is decided?
How is it decided what goes where? Huh? Okay, one last thing and we'll get to the fun stuff. Here are our two golden rules. A reference type always goes on the heap, easy enough, right? Value types and pointers always go where they were declared. This is a little more complex and needs a bit more understanding of how the stack works to figure out where things are declared. The stack, as we mentioned earlier, is responsible for keeping track of where each thread is during the execution of our code, or what's been called. You can think of it as a thread state, and each thread has its own stack. When our code makes a call to execute a method, the thread starts executing the instructions that have been JIT compiled and live on the method table. It also puts the method's parameters on the thread stack. Then, as we go through the code and run into variables within the method, they are placed on top of the stack. This will be easiest to understand by example.
Okay, so take the following method. It is a simple method. It takes integer value and add 5 to it and return the value as integer.
Here's what happens at the very top of the stack. Keep in mind that what we are looking at is placed on top of many other items already living in the stack. Once we start executing the method's parameters are placed on the stack. We'll talk more about passing parameters later.
Note.
The method does not live on the stack and is illustrated just for reference.
So add 5 p-value int integer.
Next, control, the thread executing the method, is passed to the instructions to the add5 method, which lives in our types method table. A JIT compilation is performed if this is the first time we are hitting the method. As the method executes, we need some memory for the result variable, and it is allocated on the stack. The method finishes execution and our result are returned. And all memory allocated on the stack is cleaned up by moving a pointer to the available memory address where add5 started, and we go down to the previous method on the stack, not seen here. In this example, our result variable is placed on the stack. As a matter of fact, every time a value type is declared within the body of a method, it will be placed on the stack. Now, value types are also sometimes placed on the heap. Remember the rule, value types always go where they were declared. Well, if a value type is declared outside of a method, but inside a reference type, it will be placed within the reference type on the heap. Here's another example. If we have the following myInt class, which is a reference type because it is a class, and the following method is executing. Just as before, the thread starts executing the method and its parameters are placed on the thread's stack.
So you see p-value integer here.
Now is when it gets interesting. Because myInt is a reference type, it is placed on the heap and referenced by a pointer on the stack.
So you see it's a reference type. Why? Because my int is a class, and classes, the objects of classes are reference types. Okay.
After add5 is finished executing, like in the first example, and we are cleaning up, we're left with an orphaned myInt in the heap. There is no longer anyone in the stack standing around pointing to myInt.
Okay, so this is where the garbage collection comes in.
This is where the garbage collection, GC, comes into play. Once our program reaches a certain memory threshold and we need more heap space, our GC will kick off. The GC will stop all running threads, a full stop, find all objects in the heap that are not being accessed by the main program and delete them. The GC will then reorganize all the objects left in the heap to make space and adjust all the pointers to these objects in both the stack and the heap. As you can imagine, this can be quite expensive in terms of performance, so now you can see why it can be important to pay attention to what's in the stack and heap when trying to write high-performance code.
So let's open the lecture 3 source code here. This is why when we manually coded GC, the garbage collector, our memory usage has increased significantly. Because because a dictionary is a class. You see, class. So it is a reference type. And uh, let me show you what I mean. So, for example, after we call a write dictionary to file, and if let's say if it is using a write all lines method, this will generate a string in the memory, and it will be also a reference type. So after this method is executed, since this will uh, generate a string, it will become an empty reference, an unlinked object in the heap. Therefore, it will uh, be allocated in the memory, and until we call garbage collector, it will hang in the heap, in the memory. Or let's say we are using uh, a string builder in the method. Currently, this method will be executed in the stack. Okay. However, since this method call will be included in the stack, however, when we use a class inside that method, this class will be run in the heap memory. So until we manually call garbage collector or the garbage collector is automatically called by the .NET framework, it will remain in the RAM memory, and therefore it will take unnecessary space in our RAM memory. Okay, so that is why after we have called garbage collector, our memory which has uh, reduced significantly. I will show that with example as well. In a new example, let's continue reading and then we will start examples.
Okay, that great, but how does it really affect me? Good question.
Okay, let's continue.
If we execute the following method,
So in this method call will be included in the stack. This will be included in the stack as well because this is a value type. It is integer. All these are in value types, so this will be in the stack and they will be removed as soon as method call ends.
we'll get the value 3. Simple enough, right? However, if we are using the myInt class from before, and we are executing the following method, what do we get? 4. Why? How does x, my value, get to be 4? Take a look at what we're doing and see if it makes sense. In the first example, everything goes as planned. In the next example, we don't get 3 because of both variables x and y point to the same object in the heap.
Okay, this is why. Because we have defined an x object from myInt class, and we have defined I object in the myInt class, and then we have assigned the reference of x to the I. So when we change it, the value of I, actually it also changes the value of x because the I reference to the x values, so they are basically referencing to the same value. Okay. It will be explained here. So the x is pointer and I is pointer, and their value is hold on the heap. They are not hold on the stack because they are reference types. So because they reference to the same place, when we change value, they change the same value. Okay, they are not changing the different values. So what happened to the original value of x after we assigned x to the I, actual original value of I after we assigned x to the I, the original value of I is now hanging on the heap. Actually, it was not initialized, so it was null. So that will be handled by the garbage collector.
Hopefully, this gives you a better understanding of a basic difference between value type and reference type variables in C# and a basic understanding of what a pointer is and when it is used. In the next part of this series, we'll get further into memory management and specifically talk about method parameters.
Okay, so let's see what we have solved until here. This is truly object-oriented programming, and these are objects and these are references to the objects. Okay, let's start. So let's start with explanations. Let's say value type test. Okay, so this button will test value type. Okay, and I am going to make a for loop 100 million times. Okay, so 100 million times I am going to generate in 64. Well, actually I'm going to make a random. So let's make it static, so it will be remaining on the entire application, probably in the heap as well, because it is a class. And then next, let's make this double. Double is also a struct, so it is a value type because structs are value types. you see when I hover that, it shows system.random and it shows struct system.double. Okay, so here I am going to generate 100 million, let's say double variables. What we want to achieve with this is a method. This button call is a method, so this will be executing in the stack. Okay, so let's run it and see the how memory there will be a memory increase or not, because each time when a new value assigned, it will be always using the same value. Okay, it will not generate a new value in the stack. Let's see. Okay, application will pass. Okay, you see it is run 100 million time and no memory increase has happened. I am running it again and it is again run 1 million time. Okay, so let's add another method to make a comparison. Okay, and let's make it test. Let's make this rename it as value type memory test and reference type memory test. Okay, and when I double click on it, it will generate the click button event here. Okay, this time I'm going to use a class. Okay, so let's say it will be public so that other classes can access. Okay, so this time this double will be inside the class, therefore it will be held in the heap. So I'm going to copy paste this, and this time I'm going to compose a my class double value, and it will be as new my double class. And inside it, I will make an assignment like this. Debuggable equal to my run value, and see whether there will be any difference or not. Each time this will generate a new object and the previous object will be hanging in the heap. So until the garbage collector kicks in, it should stay in the heap. Okay, value type memory test. Okay, nothing, no memory increase. And let's try the class type. Okay, it also didn't increase because it has always generated a new class. So what I am going to do is making something different. Okay, I'm going to make it like this. I'm trying to okay, when I say new double, it will generate a new and it will overwrite this one as well, probably. Let's try this way. I am trying to uh, make those references lost. Oh, I know what I'm going to do. Oh, okay. I'm going to make 1 million times a method call. and inside this I'm going to make this. So let's try this method call. This time it will be hanging in the memory. It will not be cleared after this method call is ended because it is a class type. It should hang in the memory until garbage collector kicks in. Okay, still it didn't make any difference. Perhaps the double is not taking much space, but 1 million should be. Okay, perhaps we should use a string for this. Let's add a string. And some long text. Let's make it. Okay, let's try this way. Okay, so looks like garbage collector is working very well. I wonder if we can pause the garbage collector. Okay, there is start line no region. So how it works? Okay, let's try this way. Maybe this will prevent garbage collector running. Let's try this way, by the way. Okay, let's see. Let's do a performance profiler and see what happens. I'm going to use memory usage performance type. You see it shows object difference, heap size difference, and I'm going to start the project analysis start. Let's make a start. You see it is making a garbage collection all the time. You see it says small object heap allocation. Okay, so you see the garbage collection count. Okay, it has made 10,000 times garbage collection. And if we run the value type, I wonder if will it make any garbage collection. Okay, no. When I run the value type, it makes almost no garbage collection. Okay. Okay, so this shows clearly why we couldn't increase the RAM memory usage. Perhaps I wonder if we can disable. Okay, this doesn't work. How does this work? I wonder. Total size. It says. Okay, so this is in bytes. Okay, let's try this as bytes, kilobyte, megabyte, gigabyte, bytes, kilobyte. Okay, this is 1 kilobyte, 1 megabyte, 1 gigabyte, and this. Okay, so what it says. Okay, let's make it 3 gigabyte in this case. Or let's make it bytes. Only, okay, let's try this way. I'm going to start another test performance profiler. Let's see will it kick garbage collector again or not. Okay, there was some garbage collector, and when I click this, okay, looks like the garbage collector has failed. Okay, why did it stop? Okay, so without garbage collector, I believe it has crashed. Let's try again. It says it was too much. Let's check the link it provides. So max value is okay. Let's make it 1 million. Okay, it worked, but I think it didn't make. Stop it. Let's try 10 million. Okay, let's try with performance profiler to see. Okay, it still happened. So we didn't get what we wanted. Let's find a good example. Okay, so I think there is example. Okay, here. Okay, let's try this. Let's see if it works. Hmm, Let's let's make it like this. Oh, okay. Okay, it worked for a while and then I think stop. So let's make it even bigger. If I stop the garbage collector, it will hang in the. Oh, it is too late this time. So this is okay. Let's make it three like this. I think it will work. Maybe it is because I am out of memory. I'm not sure. Yeah, you see, we can increase the memory usage here. So the garbage collector happened there. Okay, so if I could set it higher amount of memory, it would have worked. I think this is a very good article, so I'm going to add it here. Here. So how much RAM I have? Okay, I have some more memory. Maybe now I can assign like this. To show you a better example. Okay, you see now we could reach 500 megabyte. Let's try the same with the struct. I wonder will the same thing happen or not. So here it is value type, which is struct. Integer is a struct. And let's see what happens. Double is also struct. Let's see if the RAM memory usage increases. If we could stop the garbage collector, it would fill the memory immediately. Okay, this also happened for stack. Oh, on stack it remains until the garbage collector hits. Okay, so in both way they. Oh, of course. In stack it also still keeps memory until the stack is uh, erased. It will hang there. Okay, so garbage collector is extremely important, and until garbage collector is called, uh, that thing will remain in the memory. So what determines when will be the garbage collector run? It is totally up to .NET Framework. You can manually call it, or you can let it stay to be called automatically. So let's start with what does reference type do, and what does oh, it is too much already. We'll continue from here next week. Try to understand what we have seen this week. Try to repeat codes and read again. Hopefully we will continue next week from where we are left in here. So end of lecture. I am going to upload this to the our repository. I have purchased a professional microphone to improve my voice quality. I have been struggling to fix it, however, I have failed, so I have purchased a professional microphone. I hope when it arrives, my sound will be much better. And we are always looking for volunteers to fix the subtitles, correct them. Stay safe. Hopefully, see you next week.